All right, calculus, time to start a new section, a new topic. As I've mentioned before, the limit of the difference quotient using the definition of a derivative is a bit cumbersome, kind of takes a long time. So there are shortcuts. We're going to start learning the shortcuts. So what I want to do in this video is start with the simplest possible functions we can look at, figure out what their derivatives are, and then we're going to get more complicated with higher. We're going to look at power functions with positive integer powers. And we're going to observe a trend, a pattern, and then we'll generalize that pattern to a rule called the power rule, and then we'll start using it. This is the first rule I want to learn you in a sequence of rules that we will be learning in chapter 3. So let's start with the simplest function we can think of. I want to start with the function 1. The constant function 1. If you draw a graph of it, it looks like this. It's a horizontal line. So let's ask the question, what's the derivative of 1? I want to fill in that blank right there. What's that going to be? Well, in order to figure that out, we might want to look at the limit of the difference quotient. Remember this? Well, in our case, if the function is just 1, it's just going to be the limit as h approaches 0 of 1 minus 1 over h. And this is just 0 over h. It's 0. It's always 0. And looking at the graph, no matter what point you pick on that graph, the slope is always 0. So this is one of the simplest functions we can have, and it's the simplest answer. The answer is just 0. So the derivative of 1 is 0. Okay, next, let's look at the derivative of x. Okay, so we're going to have the limit as h approaches 0. We're going to have f of x plus h. If our f of x equals x, f of x plus h is just x plus h. And then minus f of x, which is just going to be x all over h. We have that. And you'll notice the x's are going to cancel out. So we have the limit as h approaches 0 of h over h, which is just the limit of 1, which is 1. On a graph, the function does this. That's the y equals x function, and you'll see that slope is always 1. So this equals 1. Okay, so far we had the limit of 1 is 0. The limit of x is 1. What's next? Let's see what else we can do. Let's look at the derivative of x squared. Okay, so for this one, we'll look at the limit as h approaches 0. Our x plus h is going to be, f of x plus h is going to be x plus h squared, because the f function here is the squaring function. And then we'll do minus x squared, okay, all over h. So that's what it'll look like when we set up the limit of the difference quotient. What happens here? Well, we can expand this power, x squared plus 2xh plus h squared minus x squared all over h, and we'll find the x squareds cancel each other out. Okay, this ends up being the limit of 2xh plus h squared over h, but we can factor an h out. 2x plus h Then after canceling h's, we just have 2x plus h. And remember, h is approaching 0. So this is just going to be 2x. There's that. So it makes sense that it's a variable. It's not always the same because, again, if I look at the graph, my x squared function is this parabola. Its slope is not constant any longer, right? So with this function, constant function, the slope is always 0. With the x function, the slope is constant because it's a line. With the x squared function, the slope is not constant, it's changing, and therefore its derivative is not a constant function either. Derivative is dependent on x. Okay. All right. Do one more. I believe I have already done this next example. We showed in a previous video the derivative of x cubed is 3x squared. And let's keep going with this pattern. If you do the same approach with the derivative of x to the power 4, you get 4x cubed. The derivative of x to the power 5 is 5 times x to the power 4, and so on. So are you seeing the pattern? The pattern can be described like this. I'm going to put a dot, dot, dot. Down here, I'm going to write the power rule. The pattern is the derivative with respect to x of a power of x, x to the power n, where n is any number, in fact. So far, I've shown it to you with positive integers, or 0. If you have the derivative of x to the n, it turns out it's always going to be that n itself. There's 5 up here, here's a 5 out here, for example. Okay, so it'll be n itself multiplied by a power of x, and the power of x you multiply by is always 1 less. Okay, so from this 5, you get 4. It's always minus 1, right? 5 minus 1, minus 1 over here. 5 minus 1, you get 4. 4 minus 1 to get 3. So this is n minus 1. And that's the power rule. So this is a lovely shortcut for finding derivatives of powers of n. Now, what I have shown you here is not, strictly speaking, a proof, not even loosely speaking, a proof. This is just, hey, look, here's a trend, right? You can see a proof of the power rule in the textbook, and it's not that far beyond what we have learned. It's just a bit cumbersome. It uses the binomial theorem, which you may have studied in pre-calculus. But it's nice because it gives you a generalization of this to any positive integer power. In the next video, I'm going to show you that, in fact, this works not only for positive integers, but also any real number. That means negative integers, fractions, even irrational numbers. It actually works for any number. So we'll look at some more examples in a moment.